We're going to pick up where we left off on Wednesday in developing this density of states function g of E. Clearly it's a function of E of energy, and as we said Wednesday, it's going to be the number of states per unit volume per unit energy. Now looking ahead, what we'll do is we'll actually multiply this times the probability of a state being occupied. The probability is a function of energy of a state being occupied, and then integrate that product over E, over energy, so that this per unit energy will drop out and we'll end up with the number of states that are occupied per unit volume. So that's going to give us the number of particles per unit volume, the density of charge carriers. All right, and as we said on Wednesday when we started in on this, we're going to develop this thinking in terms of a large box, a particle in a box, and we have a three-dimensional box. We'll just consider it a cube, so each side is the same physical dimension. So we can have a large box that would be our define where our particle is confined, and so this would be our semiconductor, and it's A by A by A, and those are just dimensions of length. That's our box that the electron is confined to be in. And from the particle in a box, or the infinite potential well problem, we know that the energy is quantized, and there are three integers which determine the quantized energy level. And for our three dimensions, x, y, and z, we've got n sub x, n sub y, n sub z. They will be integers, 0, 1, 2, 3, and so on. And the energy of each of the state is given as E is E sub nx, y, nx, ny, nz is h bar squared pi squared over 2ma squared. So there's our a, the dimension of our box. N sub x squared plus n sub y squared plus n sub z squared. Moreover, we know that the wave number k it's actually in here. We have k is square root of kx squared plus ky squared plus kz squared. You get this from the separation of variables technique as you're solving Schrodinger's equation. And this kx, ky, kz n sub x pi over, what's this, y z over a. So we can see that this is actually h bar squared k squared over 2m. All right, so for each integer, positive integer, that gives us an energy, and it determines a value of k also. So we can think of this in terms of thinking about a three-dimensional space, not in x, y, and z, but in kx, ky, kz. So this will be k space. So for a given point in k space, that point there is kx, ky, kz for a certain combination of nx, ny, nz. And then the size of that cube, well, let's see here. On this side will be delta kx. So here's our coordinate system. Kz kx, ky, so we have our coordinate system in k space. And so this delta is delta kx, here is delta ky, this is delta kz. And then there will be another point that's in the next cube over, above, below, behind, all around. What then is the volume that we can associate with this point? This point here represents a state with valid combination of k's, and then the overall value of k right here would be k. The length of this vector from the origin in k space out to this point, representing a state, is k equals the square root of kx squared plus ky squared plus kz squared, which we just wrote down. So this is our k, our vector, you might say, in k space. And then associating a volume with the state there in k space, what is the volume we can associate with an individual state? Well, we know that these valid values are integer multiples of pi over a. So that tells us really that delta kx and delta ky and delta kz are all pi over a. Each one of those is pi over a, so we get pi over a cubed as the volume of this cube in k space. Now if our original cube in regular space were not a cube, or some rectangular, didn't have all the same side lengths, then this would be have the different side lengths in it. But we've assumed it's a cube, so simplifies it a little bit. All right, so what this means is we have one state per this volume in k space. So we have one state per pi cubed over a cubed in k space. Well, this means that if we think back to our original cube, it has a volume of a cubed. So this is the volume in regular space over pi cubed. So this is the number of states per unit volume in k space. Now let's continue to draw a picture of this, develop our picture. And I need to redraw my picture in k space a little bit. And we are interested in positive values. So we go along here, we have positive values of kx, positive values of ky, positive values of kz, and they're arrayed all in this volume, of this octant of k space. Now, what is the number of states? Okay, but now we've got our k, and we can think of a sphere, only it's an eighth of a sphere because we're in one octant of k space, and we want to go from k to k plus delta k. So we go from one sphere out to another sphere with a distance dk. So we have a shell in k space.